Tragedy strikes a bustling Canadian shopping mall.
There was water flowing, bells were ringing. I knew it was serious.
In Missouri, a massive mountaintop dam fails in record time.
When we arrived, it just looked like a different planet.
In Australia, disaster as a towering inferno takes hold in downtown Melbourne.
This spread in less than 6 minutes to 23 floors. Unprecedented, unheard of.
And in Arkansas, an oil spill threatens an entire community.
We want to protect it at all costs.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. When it comes to big construction, engineers always have to consider the elements. Fail to do so, and the results can be disastrous. Like this shopping mall in Canada that was hiding a deadly design flaw.
Once the leaking started, it never stopped. It continued until the mall actually collapsed.
An engineering disaster that left many questioning whether this could have been avoided.
They knew about it. This didn't have to happen.
And a tragedy that left a community reeling.
It was very hard to take it all in. It was pretty overwhelming.
In the wilderness of Ontario lies the remote city of Elliot Lake. Until 1955, it was relatively undeveloped.
In the 1950s, geologists discovered huge deposits of uranium, attracting mine workers from all over the globe. Elliot Lake sprung up around the mines and became known as the uranium capital of the world.
For nearly 40 years, it was a bustling mining town. But when the last mine closed in 1996, the boom times were over, and Elliot Lake had to reinvent itself to survive. Kevin McSheffrey is a local journalist.
We've gone from the uranium capital of the world to the seniors capital of Canada. 60% of Elliot Lake is over the age of 50. There's 1,000 lakes of 50-mile radius. I wouldn't want to live anywhere else. Too many people down south, and if I moved down there, it'd make it worse.
A key attraction for the aging population was its shopping mall. But this isn't the first plaza on the block. Opening in August 1980, the Algo shopping mall became the lifeblood of Elliot Lake.
Everybody met here. The food court, if you weren't here by 10 a.m., there was no room in it. It was the heart and soul of the community. There's no two ways about it.
The mall was constructed with steel beams and columns, supporting hundreds of concrete slabs, with 3 floors and a 4-story hotel incorporated into the footprint. To maximize space, the Algo Mall had a very distinct design feature. The entire roof was a parking lot.
An open rooftop parking lot isn't unheard of, but this part of Canada has brutal cold winters. Ice and snow come with the territory, so waterproofing was crucial.
Structural engineer Hassan Safarini explains.
So these are the original design drawings of 1979. It shows you the parking lot at the roof of the mall. And the most significant thing about this was the waterproofing of the concrete. When they built it, there was a new and modern approach, and that is just to seal the concrete.
The concrete panels were around 9 meters long, but only 1.2 meters wide, which meant lots of joints to waterproof.
The solution was simple. Almost 8 centimeters of concrete was poured over the entire roof, acting as a single waterproofing layer.
This concrete coating had been used, but only on much bigger slabs known as double Ts, which can be 10 times the size, meaning a lot fewer joints. With the Algo's smaller slabs, this was definitely uncharted territory.
For residents, it was clear right from the start that something was wrong.
It was leaking before the mall opened. Never stopped and just got worse.
Buckets and tarps almost became part of the mall's architecture. The leaking got so bad that some local residents even dubbed it the Algo Falls.
For over 3 decades, the parking lot continued to leak directly into the shopping mall below.
This should not happen at all. But for this to persist for 30 years is totally unacceptable.
On Saturday afternoon, June the 23rd, 2012, it was business as usual at the Algo shopping mall. But all that changed in a heartbeat. At precisely 2:18 p.m., disaster struck.
This failure was so sudden, there was no warning. The car park just dropped.
Journalist Kevin McSheffrey was in the hotel theatre critiquing a play.
There was panic there because nobody knew what was going on. At first, some people thought it was part of the play. Well, nobody has sound effects that good.
They soon discovered the truth was much more shocking.
It started with the parking lot level, dropped into the second, and dropped onto the first, right there.
Elliot Lake Fire Chief John Thomas got the call.
There was water flowing, bells were ringing, parking lot was full of people, and then I looked in the window and I saw daylight, and that's when I knew it was serious.
Even for a hardened veteran with nearly 20 years under his belt, the devastating scene that confronted John was hard to take.
And we don't know how many people are actually inside. There was asphalt, concrete. Some of these pieces of slab were as long as our truck. What really struck me was to see a vehicle inside the mall.
For 2 days, firefighters worked around the clock, searching the wreckage. 19 people were injured in the collapse, but despite rescuers' heroic efforts, tragically 2 died.
It was not a good day. Anyway, yeah, it was difficult.
In the wake of the tragedy, the Premier of Ontario ordered an immediate investigation into the disaster. As the nation mourned, everyone was asking, why had it collapsed? It was soon clear that there was one main culprit: rust. Hassan Safarini was one of the investigating engineers.
The corrosion in the mall was so severe that the closest that we could compare it to was the marine environment in terms of ships. The entire section was lost that you could see through the beam because it completely corroded.
The cause was painfully obvious. Massive corrosion of a weld on one of the supporting steel beams led to the fatal collapse.
The steel had become so corroded that it only had 13% of its original load capacity left. That one car going over it was the straw that broke the camel's back.
Well, everything was corroding, but it was the thinnest member that was likely to fail, and it did.
Now, the question on officials' minds wasn't what had happened, but why.
Why was there that loss of connection between one beam and the column that led to the collapse of the roof?
The investigation found that failed waterproofing combined with extreme Canadian winters had been slowly eating the steel away for more than 30 years.
Anywhere that has freezing winters, roads are regularly gritted and salted to melt the ice. But salt and water create a corrosive cocktail, and it's very bad news if it gets into a steel structure.
The 7.5 centimetre concrete coating was simply insufficient to prevent the salt and water from running through the many joints of the narrow slabs directly onto the steel below.
Once the leaking started in the mall, it never stopped. It continued until the mall actually collapsed.
After more than 30 years of corrosion, the heart and soul of Elliot Lake came crashing down taking more than just the mall.
After that, people started moving out of town. There was no place to shop. You couldn't buy socks or underwear in Elliot Lake.
The government report found that financial considerations played a part in the tragic failure, in what it called a toxic combination of circumstances.
Certainly it was about bad decisions that eventually led to the loss of material and then loss of section and eventually loss of life.
The Algo Mall was demolished and a new mall opened across town 4 years later, this time without a rooftop parking lot.
The simple answer to how to protect the building and to protect the steel is to prevent water from going in. And to do that, we need a waterproofing membrane. It's the membrane that protects the structure.
The original variant of the concrete waterproofing system was never used again on any project, while the empty site serves as a reminder of what happened.
It hurt the community quite a bit. And it's funny, we always talk about fire calls. Do you remember this call when? And stuff like this. This was the one call we never talk about.
With the new mall to bring people together, the residents of Elliot Lake were able to move on from the tragedy and rebuild their lives and town.
It was a tragic story. 2 women died. Hopefully nothing like that will ever happen here again.
When engineers harness the energy of hydraulics, what may look like peaceful water can become immensely powerful. The smallest mistake can have catastrophic consequences. Like this epic fail in Missouri, where a unique Mountaintop Reservoir left a trail of destruction.
1.5 billion gallons of water in a few minutes went running down this hill.
Engineering oversights combined to wreak havoc.
This thing was draining twice as fast as Niagara Falls.
And left everyone asking just what had gone wrong.
When we arrived, it almost just looked like a different planet.
The rugged Ozarks in the wilds of southeast Missouri are carved up by rivers, like here at Johnson's Shut-ins. Greg Coombs is the state park's regional director.
Here in the Ozark Mountains, shut-in is a term being the river is shut in. The East Fork of the Black River runs through Johnson's Shut-ins. And the rhyolite boulders that you see behind me form the shut-in that is a very popular recreating area here at the park.
During the summer, these rock-lined waters are a huge draw for tourists. But in the 1960s, engineers saw potential for something very different in the towering slopes. This mighty reservoir on Prophet Mountain is the power behind the Tom Sock Hydroelectric plant. Warren Witt is Director of Hydro Operations for Ameren, Missouri.
So this plant was built in 1963 is when it went into service. It actually was the largest pump storage hydroelectric power plant in the world when it was built, but it's about 100 feet deep, estimated about 1.5 billion gallons of water. The unique thing, obviously, with this reservoir is you don't see many reservoirs that are on top of a mountain.
Building on a mountaintop is always going to be hard, but there's a good reason for perching it up here. The reservoir is all about dumping water from as high as possible to generate electricity.
When built, this hydroelectric plant had a higher vertical drop than any other facility in the country, creating enough electricity to power thousands of homes.
The problem with electricity is that everyone wants it during the day and not so much at night. Conventional power stations produce electricity 24/7, but storing it for when it's really needed can be tricky.
Tom Sock can both store energy and convert it to electricity at the flip of a switch. During the day, water is dropped more than 240 meters through the turbines, providing an instant boost to the electricity grid At night, there's less demand and plenty of power available to refill the reservoir, like recharging a battery. This is known as pump storage.
We fluctuate this lake about every day. We drop it about 75 feet in elevation. It goes down, generates to the lower reservoir, and then at nighttime we pump it back full.
In 1964, this pioneering project was honored for its outstanding civil engineering. And for 40 years, it pumped power into Missouri's electricity grid. But this isn't the first reservoir on this site. What came before it met an untimely end. On December 14, 2005, Greg Coombs from Missouri State Parks was woken unusually early.
I got a call a little after 5 a.m. on the morning of December 14th that we couldn't reach our park superintendent, and there was word that there was a problem with the upper reservoir at Tom Sauk Mountain.
Initial reports were right. A vast section of wall had failed, catastrophically, and all 6.8 billion liters of water had gushed out.
When the reservoir broke and the water rushed down the west slope of the Prophet Mountain, it came into the developed zone of Johnson Shut-In State Park.
The superintendent and his family were all asleep in their home within the park boundaries when the deluge washed it away. Incredibly, they all survived.
We are extremely lucky that this event happened in December and didn't happen during one of the warmer season months when the campground would have been full.
Hydrologist Paul Rydland came to assess the damage just hours after the flood.
When we arrived, there was no identifiable trail. It was all very barren. It almost just looked like a different planet. There wasn't any trees or timber or any kind of cover like that because everything, of course, was so fresh.
This massive scar on the landscape proves just how much energy is stored in the water on top of the mountain. It was like dumping 2,000 Olympic swimming pools over the side.
289,000 cubic feet a second was the peak. Essentially, it took just over 5 minutes for that flood wave or that peak to be able to come down to the very base of this, where its junction is with the East Fork Black River.
Channeled through the turbines, that's a phenomenal amount of energy. But let loose on the mountainside, it was hugely destructive.
As we took a look at the magnitude of this water, it was actually pretty phenomenal. I was very surprised to see the force of water, and I've been 28 years in my career of dealing with hydrology and hydraulics. I've not seen anything this significant. This was a little off the charts.
An investigation was launched to understand exactly what had gone wrong. The wall had been built to survive an event like this, so why had it failed?
The old reservoir, the rock-filled dike, all the analysis said that you could overflow that top of that reservoir more than 12 hours and it would not fail. That's why there was no overflow relief structure. We had only overflowed like 10 or 15 minutes and the thing completely collapsed.
When investigators examined the damage, the reason was clear to see.
And that's where we found the rock was not compacted like most rock-filled dams are.
Not only was the dike wall weaker than expected, so were the foundations.
Where the piled rock set on solid foundation rock, the spec called for nowhere to be more than 2 inches of soil, and we found as much as 12 to 18 inches of soil in some places.
Once the water started spilling over, it quickly eroded the soft foundations, and the dike was doomed to fail. But what investigators needed to understand was why it had overflowed in the first place.
Conventional dams can be hit by unexpected water surges from a storm or an upstream dam failing, but the only water coming into this one was pumped up on purpose. Clearly something had gone very wrong.
Over the decades, the reservoir wall had settled, causing cracks in the waterproofing. To fix the problem in 2004, a new liner was installed, along with new water level sensors, known as high trip switches, to prevent the reservoir from overflowing. But no one had realized the settled wall was no longer level and the switch's calibration was off.
People that put the high trip switch didn't recognize the low point of the reservoir, and they actually ended up having it set above the low point of the wall. So it was actually overflowing the reservoir before the high trip switch could even see it.
With some cut-off switches now set higher than parts of the wall they were meant to monitor, water could spill over the low point without ever tripping the alarms.
These automated safety switches were basically redundant. The pumps kept pumping, the water just kept coming. No one knew the reservoir was overtopping.
The failure of the emergency shut-off system, combined with the weakness in the wall and its foundations, was more than the structure could handle, and collapse was inevitable. Yet the Tomsock pump storage plant was vital to the state's energy system, and in 2007, rebuilding efforts began with lessons learned from the investigation.
Once we decided, yeah, we are going to rebuild, then there became a huge focus on how are you going to guarantee this never happens again.
One key requirement was a stronger retaining wall that wouldn't settle or fail.
It was a very impressive sight to see when it was being built. I tell people it was like an ant farm. There were just hundreds of people everywhere. We had about a half a dozen concrete plants on site here, and we'd make concrete, put it right back in the same place now as a concrete dam.
The outer skin would be watertight concrete, much like the older wall. But inside, for maximum stability and strength, engineers used roller compacted concrete in place of rock fill.
One of the reasons for roller compacted concrete is you can build massive amounts in a short period of time. This gets poured about 18 inches thick, and then you roll it. And as you rolled it, it compacted down to about a foot thick, and then you just keep pouring. The roller is good for the mass and the strength and the weight to hold it in place.
In addition to the impenetrable wall, engineers developed new safety precautions.
So in this room is our emergency high-level trips that back up the normal control system. This whole building was built with the new reservoir to provide a whole nother level of protection, utilizing 6 probes in here and 2 out on the overflow relief to shut down the units in an emergency. This is now the most sophisticated level instrumentation system probably of any hydro plant in the world.
Now the Tomsock Reservoir is stronger than ever and continues to be key to a cleaner, greener energy future.
We are putting some wind farms in service right now. We've got some solar farms in service, but you need a way to store that renewable, clean energy for when we really need it. And pump storage is the biggest and best way to do that.
This is a perfect example of engineers learning from mistakes of the past. And this unique reservoir looks to be here to stay.
When it comes to creating standout structures, form and function often go hand in hand. But if one outweighs the other, it can be a recipe for disaster. Like this catastrophe in Australia, in an apartment building in the middle of the night.
It looked like a towering inferno. The whole side of the building was on fire.
The fire took hold in seconds and forced a mass evacuation.
I see a big fire. Scary, very scary.
This disaster revealed a deadly defect.
This problem was massive, not just in Australia, but all over the world.
Melbourne, Australia, is a cosmopolitan city with a rich history. Local writer Mark Murdoch explains.
The growth of Melbourne really started in the 1850s with the gold rush and really set it up for the future. At one point, it was actually the second richest city in the British Empire behind London.
As its population blossomed, so too did its architecture.
Melbourne has an incredibly diverse and eclectic mix of buildings. We have Victorian buildings dating back to the 1800s and early 1900s, and then these days to the ultra-modern skyscrapers.
In the 1990s, Melbourne embarked on a 30-year project to redevelop its once derelict docklands.
This was one of Australia's largest urban renewal projects. Everything from roads to offices and more than 10,000 apartments.
In 2011, work began on the 23-story La Crosse Tower. To stand out from the crowd, it had a very distinct design feature, an aluminium covering. Fire safety engineer Stephen Kipp explains.
Modern buildings want to use very innovative, unique, fancy-looking materials to give a really crisp, sharp edge. Aluminium has the ability to have very straight edges and have a very clean finish for a long time.
Standing around 58 meters tall, the entire building was finished in aluminium composite material, or ACM. Just over 4 millimeters thick, this cosmetic skin had a layer of polyethylene sandwiched between two sheets of aluminium.
The core material, which is usually a plastic polyethylene, was added to avoid what's called oil canning, to avoid that sort of ripple effect that metals get when they heat up in strong sunlight.
You might not have heard of it, but polyethylene is the most common plastic in use today. It's found in everything from plastic bags to plastic bottles. It's even on the outside of buildings.
The La Crosse Tower with its distinctive skin opened in 2012, and its 240 apartments were soon home to more than 400 residents. Monday, November the 24th, 2014. For one La Crosse resident, Shashi Kumar Shaw, it was just like any other day.
Monday, went to work, came back, cooked my food, went to sleep. Very, very normal day. And then the alarm started to ring.
At 2:25 on Tuesday morning, a single smoke alarm was activated on the 8th floor. Other alarms in the building quickly followed.
The alarm kept on ringing. The alarm never went off.
The fire officer on duty that night was Deputy Commissioner Ken Brown.
We originally got a call from the resident inside the building. It rang alarm bells knowing it was a residential property, but a high occupancy rate, and 2:30 in the morning, people would be generally asleep.
Shashi woke his friends and they quickly began to evacuate.
We came out from this side, and the moment I reached there and turned right, there is the whole fire. Crazy.
The building's sprinkler system kicked in. Firefighters were on the scene in less than 5 minutes.
The whole side of the building was on fire and it was spreading up to the roof.
The front of the building was ablaze and rising rapidly.
This spread in less than 6 minutes to 23 floors. Unprecedented, unheard of before.
Within maybe a minute, a minute or two, the fire quickly went up. The fire was massive, massive.
With a towering inferno on their hands, Ken and the rest of the Fire Rescue Victoria team went to work.
At the height of the blaze, we had 22 fire trucks. We had 4 specialist appliances. We had ladder platforms and support vehicles as well.
Within 30 minutes, amazingly, firefighters had this 16-story blaze under control, and more importantly, had the residents out.
There was more than 500 people in the building at the time of the fire. Fortunately, they were all evacuated, and there was only 3 minor injuries, so it was a good outcome.
Thanks to internal sprinklers and the fast-acting fire service, tragedy was avoided.
After seeing that fire and coming to know that there was nobody killed, I thought that we were very lucky.
When the flames died down, questions were being asked. How had this building fire spread so high, so quickly? In the aftermath of the blaze, Fire Rescue Victoria sent investigators in to determine the cause of the catastrophe. Deputy Commissioner for Fire Safety, Michelle Young, explains.
There's many avenues for the fire investigators to gather information, and unless you know what you're looking for, it just looks like all that stuff.
Analysing the damage, the team discovered that the fire started on an 8th floor balcony, with a cigarette butt discarded in a plastic yoghurt pot.
That cigarette caused the yoghurt container to catch alight, which in turn caught the table alight, and those embers got into the air conditioning unit, which then in turn caught the cladding, and then it just shot up from there.
That cigarette might have been the initial trigger, but the speed at which the blaze spread up the cladding gave fire chiefs real cause for concern.
What is this material? Why did it spread so quickly on the external? What's out here that's different?
The covering was sent to the CSIRO, one of Australia's leading scientific research institutions. Fire engineer Alex Webb analysed the samples.
The fire brigade actually asked us to do some testing on the cladding that was on there, and one specific test they asked us to do, which was the AS 1530 Part 1 test, which is about its combustibility.
The standard temperature for the test is 750 degrees Celsius.
The aluminium cladding samples that we received is something similar to this. It's not the actual one, so it has two skins of aluminium with the polymer core in the middle. So to make it for a sample we're going to be able to test, we need to cut it into discs, because we have to make a sample. It's actually this shape, about the size of a fist. In the pictures, we can see the sample here, sitting on top of the furnace, which is kept at 750 degrees C, really stable temperature. If there's any flaming, or if the temperature of the furnace goes over a certain criteria, then we know that the material is actually combustible.
What Alex and the CSIRO team discovered was shocking.
In the photos here, we can see the flames actually coming out of the furnace. This is a photo when the material was extracted and is still flaming.
The conclusion was that this material miserably failed industry standards. Fire safety engineer Stephen Kipp explains.
The cladding included a highly combustible polyethylene core. In fact, the CSIRO found that a test that should have lasted 20 minutes failed after 93 seconds.
So why was a highly flammable material wrapped around an entire apartment building? It turns out that this covering was not actually approved on the building permit.
The cladding that was planned for the lacrosse tower had a mineral fiber core, which is fire retardant, but the polyethylene core was not. The difference in combustibility is massive.
Polyethylene has a very high calorific content, so it's very energy laden. So once it's ignited, it can burn by itself. Now, fires like to burn upwards. If you can imagine, if you lit a match, if you turned the match upside down, it would burn very quickly. So any situation where combustible plastic is in a vertical situation means that the fuel is ahead of the flame and the fire will spread rapidly.
The apartment building was a potential ticking time bomb, and the single cigarette butt was the fuse.
With combustible cladding, it's like wrapping a building in flammable liquid, virtually, and the spread of fire is so quick, and with the melting aluminium, it drops down and creates fires on lower levels, which is something we don't see very often.
It's like the difference between putting bricks on the outside and putting cardboard paper on the outside. You know, we know which one's going to burn more readily and we know which one's safer.
Further investigation revealed that this highly flammable material, although non-compliant throughout Australia, had been used on buildings across the country for years.
In this case, it was the cheaper, easier to build product that is actually quite combustible that was used, I think, in error by the people who constructed the building.
While narrowly avoiding tragedy, the disaster prompted an overhaul of the state's building safety regulations.
That opened up an audit of about 170 other buildings in Victoria, and we've since had a Victorian cladding task force where nearly 1,700 non-compliant buildings have been discovered. So this is an ongoing long-term issue.
That's one of the benefits that have come out of this, that we've identified these buildings and they are now registered and we can work with them to help reduce this material and help make Victoria a safer place.
In 2019, nearly 5 years after the fire, the non-compliant covering on the lacrosse tower was finally replaced.
Ultimately, people have to feel safe in their own homes, and hopefully now action will be taken to prevent this and related tragedies from ever happening again.
When massive feats of engineering fail, many come crashing down from above. But sometimes the real danger lies in what lurks beneath. Like this catastrophe in Arkansas.
It was surreal, to say the least. I would not have expected that then or now.
A river of oil engulfing a town.
Incredible, and that is oil.
In its path, one of the best fishing lakes in the entire state.
The oil came into the upper end of Dawson's Cove. We want to protect it at all costs.
The town of Mayflower, Arkansas, sits on the banks of Lake Conway. In a state that prides itself on natural beauty, this nearly 13-kilometre man-made waterway is a huge draw for both tourists and residents alike. County Judge Alan Dodson has lived here all his life.
Well, Lake Conway has always been special to anyone who lives around here. It's the largest state-owned game and fish lake in America. Just a natural reserve for wildlife. It's just beautiful, and we are proud of it.
Lake Conway was created for one main reason: fishing. Not only is it a world-class destination for anglers, migratory birds stop to fish here too.
Developed back in the late 40s, this man-made haven was a major attraction to the Mayflower community. But less than a decade ago, an engineering blunder almost destroyed it. On March 29, 2013, Mayflower resident Drew Barnes was driving his daughter home.
The closer we got to the neighborhood, there was something that was very wrong. I saw a stream, and I assumed it was water gushing down the opposite side of the road.
Drew started filming.
It took me probably 30 seconds to figure out that that wasn't water. There was obviously something else there.
That something else was heavy-duty crude oil.
To get into the neighborhood and find an oil spill was very shocking and very sobering. It was disbelief, I think, but given all the other sensory input with smell and eyes burning and all of those things, you know, it was surreal, to say the least.
Thick, heavy, and toxic. Nearly 400,000 litres of it was spewing onto the streets.
Incredible, and that is oil.
The equivalent of thousands of barrels of crude was moving fast, flowing into storm drains and heading towards Lake Conway. Judge Alan Dodson and the community swung into action.
So we're on Arkansas Highway 89, so the oil has to get under this highway to get to the open water of the lake.
With time running out, Alan and the team knew they had to block the pipes to protect the lake.
We're not industry experts, but we're the first on scene, and we have our own skill sets. We knew that we could create a mechanical block here and that no water and oil could get from the cove into the greater part of the lake.
If they could create a makeshift dam, the lake's wildlife could potentially be saved.
We had dozens of people working on covering these culverts with gravel. We covered the end of the pipe up with multiple sheets of plywood. The barricade was successful, but nothing could get through them.
Amazingly, the community's rapid response saved Lake Conway from a massive ecological disaster.
I think in the heat of the moment, you don't have time to stop and think about, small victories like that. But, knowing we got that block, that was a huge relief.
Although Lake Conway was in the clear, much of the surrounding area was contaminated. More than 1,000 meters of containment booms were deployed to trap the oil. In the town, 22 homes had to be evacuated. The shocked Mayflower community wanted to know what had caused this catastrophe. The answers lay buried beneath the ground.
There are around 300,000 kilometers of pipeline crisscrossing the U.S., carrying oil and gas 24/7 from drill sites to refineries and onto all kinds of industrial facilities. And one of them runs straight beneath Mayflower.
It's part of the mighty Pegasus pipeline.
The Pegasus pipeline carries 90,000 barrels of crude oil a day, almost 1,400 kilometers from Illinois to the refineries of Texas. Some of it runs on the surface, but miles of pipeline are buried underground.
Never had any concern about the pipeline or any pipeline, you just know there's something there, and of course you hope nothing ever happens to it.
Nothing until that day.
The pipeline had clearly burst. It was hemorrhaging oil at an alarming rate, and Mayflower bore the brunt.
With the pipeline shut down, engineers were quick to the scene to assess the source of the rupture.
One section of a pipe had a nearly 7-meter split running lengthways along the top of the pipe. There was no other damage, so this crack was clearly the cause. The question was, why had it failed?
The investigation revealed that the problem could be in how the pipe was made about 60 years before the accident.
One of the simplest ways to make a pipe is called seam welding. You roll a sheet of steel into a cylinder and weld this seam. In this case, using electricity to melt and join the steel.
Gary Prins is an associate professor of engineering.
So they take a sheet of steel and they essentially cold work it to more of a cylindrical shape, and then they pass an electric current along the two edges of the plate just to heat them up, and then force the ends of the plates together. The fusion of the two plate edges is very important.
In this case, the particular method used was known as low-frequency electric resistance welding. Now obsolete, it was discovered to be susceptible to defects such as seam corrosion and inadequate bonding.
These pipes have a problem. The heat from welding that long seam together can create defects in the metal around it. And those defects could join up to form fatigue cracks.
What happens when we have defects in there is they cause stress concentrations. And so at the tips of these cracks, we get very, very high stresses. During repeated loading, these cracks, even though the loading is insufficient to just fully rupture the pipe, they can cause growth of the cracks over time. And these cracks can grow to a point where they become critical and unstable.
Although phased out in the 70s, these aging pipes were still part of the pipeline running directly underneath the town.
When you pump oil through a pipeline, the pressure fluctuates. When it's happening day in, day out, the stress fatigues the metal, and it's only a matter of time until it fails.
As we repeat this stress over and over, the cracks grow until they maybe merge with another crack, and then that crack gets much bigger, and then eventually they might reach a point where they reach that critical size and can cause a rupture.
After years of transporting heavy-duty crude, the seam and the welding finally gave way, pouring out oil onto an unsuspecting neighborhood, leaving a trail of destruction in its wake.
The two houses that were closest, those are completely gone. So, it carved a path essentially to the lowest elevation and down into the watershed and did some real damage. Obviously, these houses are just gone.
After the disaster, the ruptured section of the pipeline was isolated and repaired, and a massive cleanup operation began.
This was one huge and costly mess, but thanks to a swift response and an epic cleanup, Mayflower and Lake Conway was safe again.
At the time, you wouldn't consider that being risky in any sense of the word. There's pipelines buried all across the United States, and it's stranger than fiction.
With a new electric welding process now common practice, creating higher quality welds, hopefully disasters like this are a thing of the past.
Well, I'm thankful that it's back to its natural state. Of course, we're proud of our wildlife, we're proud of our nature, we're proud of our clean air, we're proud of where we live. We want to protect it at all costs for future generations.